Hi AP Stats. Today we're going to begin Lesson 9.2, Day 1. And our learning targets today are to state and check the random 10%, which is the independent condition, and large counts, which is your normal condition, for performing a significance test about a population proportion. We're also going to calculate the standardized test statistic and p-value for a test about a population proportion. So, are we sure that Mrs. Cowles is not a good free throw shooter? So in Lesson 9.1, we use simulation to estimate a p-value to decide whether or not Mrs. Cowles was exaggerating about her free throw percentage. Today we will use the formula to find a p-value. Now, if you remember what a p-value is, it's a conditional probability. It's the probability that your sample data occurs given that your null hypothesis is true. So I'd like you to go ahead and start to look at the problems. You can pause the video and see which ones you can answer. If you remember from lesson 9.1, I made the claim that I could shoot free throws with a proportion of makes being 80%. So I want you to begin by writing your hypotheses. So your null hypotheses should be HO is P equals 0.8, and the alternative hypothesis is that my true proportion of free throws is probably less than 80%. So we said less than 0.8. When you are establishing your hypotheses, you always need to state what the parameter is, and the parameter is the true proportion of free throws Mrs. C makes. Now, each class found a different p-value because each dot plot was different. Would it be appropriate to use a normal distribution to model the sampling condition or the sampling distribution of p hat? Now, when we are going to do the normal condition, we need to check the large counts. Now, when we did confidence intervals, we didn't know the true proportion value, and when we did large counts, we would do n times p hat being greater than or equal to 10. And then we would check n minus times 1 minus p hat to be greater than or equal to 10. But now this is different. Here, we are going to accept the null hypothesis as being true. So if we accept it to be true, we are expecting that 80% of the free throws will be made. So since we believe the null hypothesis to be true, we will use the p-value from your null hypothesis when checking the normal condition, your large counts. So to check to see if it's going to be a normal distribution, we're going to do n times p is greater than or equal to 10. So we have 50 times 0.80, which is 40. That's greater than or equal to 10, so that's check. That checks off. And then we have n times 1 minus p is greater than or equal to 10. So we had 53 throws, 1 minus p is 0.20. That'd be the number of failures. So 10 is greater than or equal to 10, so therefore it checks. So it is appropriate to use a normal distribution to model the sampling distribution of p hat. What are the other conditions that we check? Well, as we did with the confidence intervals, we still have to check the random and our 10% condition, which is our independent condition. When we sample without repeating, we have to check the 10% condition. So, now that the conditions have been met, find the mean and standard deviation of the sampling distribution of p hat. Well, if we remember, the mean of our sampling distribution p hat is equal to the the mean of our sampling distribution for p hat is equal to the parameter p. Well, since we are assuming the null hypothesis must be true, p is going to be equal to 0.8. To find the standard deviation of p hat, we use the formula p times 1 minus p over n. And again, we use the p-value because we are accepting our null hypothesis. We are expecting that 80% of the free throws are going to be made. So you're going to go ahead and calculate those, and you're going to find a mean of the sampling distribution to be 0.8 for the parameter p, and then you're going to find the standard deviation for p hat to be 0.057. Again, pause the video as needed to copy things down and make corrections. So now we're going to use the mean and standard deviation you found to label the normal curve. So you have this normal curve here, and we know the mean of our sampling distribution, 0.80, is going to go in the middle. And we know that the standard deviation is 0.057. So for each standard deviation to the right, you add 0.057. For each standard deviation, you go to the left, you subtract 0.057. So you have your curve labeled. Now, the question says, how many standard deviations below the mean is p hat of 0.64? Now, here's our p hat, 0.64. Okay, we're going to put that on there. And I can see where it curves in my curve, somewhere between 0.629 and 0.686. It looks like it's going to be between 3 standard deviations below and 2 standard deviations below. So to find the number of standard deviations below, we're going to calculate the z-score. So we're going to take p hat, our statistic, we're going to subtract our true proportion that we are expecting to be true, 0.80, and we're going to divide it by the standard deviation, and we get negative 2.81. So if p hat is 0.64, it should be 2.81 standard deviations below our mean, and we can see that that occurs in our curve here when we draw where 0.64 would be. So the question says, what is the probability of an 80% shooter making 32 out of 50, our p hat of 0.64 or less? And again, we always go in the direction of our alternative hypothesis. Remember, I only made 32 out of 50 free throws, so the p hat was 0.64 for our sample data there. So we will look at it at 0.64 or less because that's the direction of our alternative hypothesis. So we shade that in on a curve. Now you have 2 ways you can answer this question. You can use table A and find the z-score on table A, negative 2.81, and use the z-score, and you'll find that p is equal to 0.0025. Or you can use your calculator. Now again, when you use your calculator, you have to have your picture drawn out. You have to have the normal stated with the mean and standard deviation labeled, and you have to have your p hat labeled in the area shaded where you're going to find your probability. So p is equal to normal CDF. It's to the lower to the left, so we just can use negative 1,000. Our upper boundary is 0.64. Our mean is 0.80, 0.057. Using the calculator, you should come up with the same number. Okay, so what conclusion can we make? Well, since our p-value is 0.0025, and we see that is less than 0.05, okay? And again, we use a significance level of 0.05 or 5% when a significance level isn't given to us. So since our p-value is less than 0.05, we have convincing evidence against the null hypothesis, and we can reject it. So basically, we were trying to find the probability of an 80% shooter making 32 out of 53 free throws or less if it's true that they are an 80% shooter. Well, if it's true that I was an 80% shooter, the probability of me making 32 out of 50, given that I'm an 80% shooter, would be 0.25%. It's very unlikely, and it's below our significant level. So therefore, we have convincing evidence against our null hypothesis and are going to reject it. So then we need to make a statement about what evidence seems to be showing. So therefore, it appears the true proportion of free throws made by Mrs. C is less than 80%. So we have to reject the claim that I am an 80% free throw shooter. Okay, so let's summarize the important ideas for a significance test for P. The first one is our learning target number 1, is that significance test for population proportions, the conditions must be met. In order to run the significance test, we have to have the random condition be met. Data should come from a well-designed random sample or a random assignment in an experiment. Otherwise, we can't infer upon a population or establish cause and effect if it was an experiment. We also have to check the independent condition. Sampling without replacement for the population allows us to use standard deviation formulas. Or if we're sampling without replacement, we must meet the 10% condition for independence. Now, I always like to show that as 10 times our sample size will be greater than the population size. For our normal condition, the sampling distribution of the statistic is approximately normal. So for hypothesis tests, we start by assuming the null hypothesis is true. So we will use P, the population proportion we are assuming to be true from HO. Now, this says here, and I'll even zoom in maybe a little bit so you can see it better. Nope, I guess it won't let me zoom. Okay. Your textbook will label P from your null hypothesis as it looks like a P sub 0. We call that P naught. As you go ahead and look in your textbook, anytime they're going to be talking about P from the null hypothesis in formulas, they're going to call it P naught. The AP formula sheet just uses P. Okay? So if you see P naught in formulas, it's equal to your p-value from HO. They are the same thing. I'm actually going to pause this for a second, and I'm going to pull up the AP formula sheet so that you can see that. So give me 2 seconds. Okay, so here's your AP formula sheet and what this is going to look like when you're having to find the parameters of a sampling distribution. It says the mean of p hat is equal to p. In your textbook, it may say the mean of p hat is equal to p naught. Again, p naught is the parameter from your null hypothesis. On the AP formula sheet, you're going to see it written as the standard deviation of p hat is the square root of p, the parameter from the null hypothesis, times 1 minus p over n. If you go back and look in your textbook, they use p naught. So they have changed this on the formula sheet, so that's why in the notes I am showing you this way with the p-value, but you want to know that the p-value is from the parameter from your null hypothesis, and your book will just call that parameter P naught. Okay, so let's see how you did on the check understanding. So according to the U.S. Census Bureau, the proportion of students in high school who have a part-time job is 0.25. An administrator at a local high school suspects that the proportion of students at her school who have a part-time job is less than the national figure. She would like to carry out a test at the significance level of 0.05. The administrator selects a random sample of 200 students from the school and finds that 39 of them have a part-time job. So, state the appropriate hypothesis for performing a significance test and be sure to define the parameter of interest. So, our null hypothesis is that P is equal to 0.25. The alternative hypothesis is that P is less than 0.25, and P is the proportion of high school students who have a part-time job. Again, important that you always define what your parameter is. Explain, why does the sample result give some evidence for our alternative hypothesis? Well, 39 out of 200 is 0.195, which is less than 0.25. Check if the conditions for performing the significance test are met. So the random condition is met because it tells us we have a random sample of 200 students. The 10% or the independent condition is met because it's 10 times 200 is less than the population of all students at the school. So 2,000 is less than the population of students at the school. That's reasonable to assume. And then normal, our large counts. Again, we're going to use P, aka P naught. So it's 200 times 0.25, which is 50, greater than or equal to 10, that checks. 200 times 0.75 is 150. That would be greater than or equal to 10, so it checks. So now calculate the standardized test statistic and the p-value. So the test statistic is the z-score. So we're going to take p hat minus p naught. And again, it should just be p because that's how they write it on the AP stats formula sheet. So our statistic was 0.195 because it was 39 out of 200. Minus, we're expecting our null hypothesis to be true, minus 0.25 over 0.25 times 0.75 over 200. We take that square root. So these should be your values. And when you come out with that answer, it's negative 1.80. So our test statistic is negative 1.80, means it's going to be below the mean and a little over almost 2 standard deviations, not quite. So now we're going to go ahead and we're going to draw our normal curve. We're going to label it normal with the mean of 0.25, 0.036, label the mean and standard deviation. Put your mean on there. Go ahead and put where 0.195 would be. And we are going to shade everything to the left because we are finding the percentage of our from our data and in the direction of our alternative hypothesis, which is less than 0.25. So our p-value for our sample data is going to be normal CDF, and since we're going to the left, it's negative 100, 0.195, 0.25, 0.036, so it's approximately 0.036. That should be your p-value, so it's about 3.6%. What conclusion can we make? Well, our p-value is less than our significance level, so this is significant, meaning it's unlikely to occur by chance given our null hypothesis being true. Given that the true proportion is 25% or 0.25, it is unlikely that this data, the sample data of 39 out of 200, which is 0.195, would occur by chance. So we have convincing evidence against the null hypothesis, and we're going to reject it. So then we're just going to state, it appears the proportion of high school students at this school who have part-time jobs is less than 0.25. After you reject it, you want to put context back in and explain what conclusion you are making. All right, so that is section 9.2, day 1.